while clearly every Lipschitz function is not necessarily bi-Lipschitz, it is possible to decompose the domain of a Lipschitz function into sets upon each of which the function will be bi-Lipschitz. In particular, we have the following theorem called the Lip-bi-Lip theorem. So the theorem is stated for one Lipschitz functions defined on the unit cube. However, by composing our Lipschitz function with a translation dilation and multiplying it by a constant, you can see how it will generalize to arbitrary Lipschitz functions on arbitrary cubes. So suppose we're given a one Lipschitz function defined on the unit cube in our M going into a Euclidean space of dimension at least M. Then it's possible, so given the number delta, it's possible to decompose the unit cube into sets E1 through EM plus some garbage set G such that the following holds. So first of all, upon each E set, the function f is 2 over delta by Lipschitz. And then the garbage set has very small image in the sense that the Hausdorff content of the image is less than a constant times delta. And it's also important to note that this theorem is quantitative in the sense that when we specify this number delta, then the number of sets E1 through EM is a number depending on delta and the dimension of the home space, and C is a number that just depends on the dimension. So to get an idea of what's going on, let's look at an example. So suppose that we're looking at a one Lipschitz function that is going from the real line to itself, and this is its graph. Okay, this is the graph of f. So you might recall from calculus that a function is injective if it satisfies this horizontal line test, that any horizontal line touches the graph at most once. So there's a similar rule that if you have a function f defined on the real line, it's bi-Lipschitz if the slope of, so not only is it increasing, but the slope of the graph is at least some constant, and the slope is bounded above by some constant. So you can see that this function is not bi-Lipschitz, and it's since in particular right here we see that the slope is approximately 0. However, we can split the domain up into parts where the function is bi-Lipschitz. So let's say this is set E1. So we notice that along this interval the function is the graph of the function just looks like the graph of the function y equals x, and so this will be a bi-Lipschitz function on this set. Similarly, we can restrict to this set, and f will be bi-Lipschitz. We can restrict here, and f will be bi-Lipschitz. Restrict here, and let's say we restrict here. Okay, so when we restrict to each one of these intervals, we see that our function f is strictly increasing, and in particular bi-Lipschitz. Now, what happens on the remainder of the set? Well, so the remainder of the set is this garbage set G. So we'll highlight these intervals as being part of G. Okay, so notice that if we look at the images of f, the image of G under f, so we just have to look at the part of the y-axis where the portions of the graph lie. So we'll get an interval here, and if we look down here, this portion of the graph will go right here, and then if we look here, it's just a small little point here and a small little point here. So you see that the places where our Lipschitz function levels off, if we look at the projection of those points on the y-axis, it's actually a very small set, even though the set G is quite large in some places in the domain. So in the construction of the Lip-bi-Lip theorem, or in the proof of the Lip-bi-Lip theorem, we'll see that the set G consists of other parts, not just the places where our function f is moving very slowly. But this is the general idea of the proof. The proof uses a clever algorithm to partition the domain into sets where the function is bi-Lipschitz plus a garbage set. So let's go over the details. So we're going to fix some very large integer n and some small number epsilon, which we'll fix later. And we're also going to specify some families of cubes. So first of all, E1 is going to be the set of cubes where the omega number of 10q is at least epsilon. Recall that the omega number is the quantity that features in Doron-Searle's theorem, and measures how approximately affine the function f is inside the cube 10 cube. Next, we have the family of cubes E2. So it's a set of cubes for which the sum of these characteristic functions of cubes R in E1 containing Q is bigger than n. This is just a fancy way of saying that this is the set of cubes Q that are contained in more than n many cubes from the collection E1. Finally, we have the collection of cubes E3. So these are cubes not in E1 for which the Hausdorff content of the image of these cubes is small, in that it is less than delta times the Hausdorff content of the original cube. We claim that if we define our garbage set to be the union of cubes are either in E2 or E3, then the Hausdorff content of the image of these sets is small. So let's first focus on the cubes in E2. So what we're going to do is first measure the Hausdorff content of the union of cubes in E2. Now recall that Hausdorff m-dimensional content in Rn is actually equal to Hausdorff measure, which is a constant times Lebesgue measure. So this is comparable to just Lebesgue measure of the union of cubes in E2. So this is the same thing as, this is equal to the integral over the union of E2 of the function 1 dx. Now recall, if x is inside the union of E2, that means that x is contained in at least n many cubes from E1. So that means that this is at most 1 over n times the sum over R in E1 of the characteristic function of R. Because notice that if x is in the union of the cubes in E2, that means that the sum of characteristics functions of cubes R from E1, that sum will be at least n, because x is contained in at least n many cubes from this collection. And because that is at least n, that will mean that 1 over n times this sum is at least 1. So now we can evaluate this integral. This will be the same thing as 1 over n times the sum over cubes R in E1 of the measure of R. Now recall that if R is in E1, that means that the omega number for 10R will be at least epsilon, which means that this will be at most 1 over n epsilon squared times the sum over R in E1 of omega f of 10R squared times the volume of R. Okay, and that's because omega f divided by epsilon will be at least 1 for each cube R in E1. Okay, so now notice that this sum is at most the same sum if we just sum over all dyadic cubes contained in Q naught, right? And then we, as we showed with Doron-Soros theorem, this sum, if we take the sum of the omega numbers of f over all cubes R inside the unit cube, this will be at most some constant times the Lipschitz constant squared over n epsilon squared. Okay. So now what we do is we pick n large enough so that this, so first of all, notice that the Lipschitz constant in our case is just 1. So this is just at most 1. And then now we pick n large enough. So n bigger than 1 over epsilon squared, and quite a lot bigger, 1 over epsilon squared delta, so that this is less than delta. And so that implies then that the Hausdorff content of f of the union of E2 is no more than the Haus, since this is 1 Lipschitz, this is no more than the Hausdorff content of the union of E2, which is less than delta, which is what we wanted. The case of the cubes in E3 is a little simpler. So first of all, I'm going to let Qj be the maximal cubes in E3. So that means that these are cubes in E3 that are not properly contained inside any other cube from E3. And therefore, the union of these cubes is going to be equal to the union of cubes in E3, and each of these cubes will have disjoint interiors. So this implies that the Hausdorff M content of the image of E3 is going to be equal to the Hausdorff content of f of the union of these cubes. By subadditivity, this is at most the sum of the Hausdorff contents of the images of each one of these cubes. Now, because these cubes come from the collection E3, this inequality is satisfied. So this is at most delta times the sum of Hausdorff contents of these cubes Qj. Then recall that Hausdorff m-dimensional content in Rm is equal to m-dimensional Hausdorff measure, and that's a constant times Lebesgue measure, which means that this is at most some constant times the sum of the Lebesgue measures of these cubes. And because all these cubes are disjoint or have disjoint interiors and are contained in the unit cube, this is at most delta times the measure of Q naught, which has measure 1. So this is at most delta. And that proves the claim. So now what remains to be done is to sort the rest of the set Q naught, so the part that isn't in the garbage set, to sort that set into a bounded number of sets upon each of which the function f is bi-Lipschitz. So the way that we're going to do this is that we're going to come up with a function alpha that assigns to every point in Q naught a unique word. And by word, I mean a string of zeros and ones of length n prime, where n prime is going to be some large but bounded integer. And then this will give us a partition of the part outside the garbage set into sets where the function is bi-Lipschitz. Now we're going to define this, this function alpha inductively. So we're going to construct it as a sequence of, a limit of sequence of alpha sub k's. So in order to do this, we're going to let curly f denote the set of pairs of semi-adjacent cubes in E1, not contained in cubes from E2 union E3. So what does it mean to be semi-adjacent? So semi-adjacent means that, so if two cubes, Q and R, are semi-adjacent, that means that they have the same size, they're disjoint, but their triples intersect. Okay, so they aren't very close, but they're not too far from each other either. So for example, if this cube here is Q, then all the red cubes that have side length equal to that of Q are semi-adjacent to Q. So this is the picture to have in mind. Furthermore, we order the cubes in curly f from largest to smallest. Okay, so now let's, so suppose that we have defined our function alpha k, and we've come to the pk plus first pair in curly f. Okay, so we run down our list of pairs, and each time we get a new pair, we adjust the definition of our function alpha k. So let's say we've come to our k plus first pair, q and r. And suppose that alpha k currently is equal to epsilon 1, epsilon 2, dot, 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 epsilon j on q, and it's equal to epsilon 1 prime, epsilon 2 prime, dot, 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 epsilon k prime on r. So what we do is we're going to adjust these sequences by adding new digits to them. So first of all, if it happens that the lengths of these strings are equal to each other, so let's say they're both equal to, let's say they both have length j. All right, then what we do is that we define alpha k plus 1 to be equal to epsilon 1, epsilon 2, epsilon j 0 on q, and then epsilon 1 prime, epsilon 2 prime, etc., epsilon j prime 1 on r, and then we let alpha k equal alpha k plus 1 on everywhere else. Okay, so now that we pick these numbers differently, that will ensure that the points in Q and the points in R have different words. They will have different strings, no matter what additional strings that we add onto these sequences. Now, in the event that these two sequences don't have the same length, so let's suppose that epsilon 1, so let's say we got the J here, then let's say there was a 0 here, and then we moved on, and then we came to epsilon k prime. Okay, so if there was a 0 there, all that we would do is to the sequence for Q's, so if the alpha k number is equal to epsilon 1 to epsilon j on Q, then we just pick it equal 1 right here so that it doesn't equal this 0 right here. And then we leave the other sequence unchanged. And then again, we define alpha k plus 1 to equal alpha k on the remainder of the cubes. And if it was instead the sequence of zeros and ones on Q that were longer than the sequence of zeros and ones on R, then we would just reverse the roles and pick the next number in the sequence for R so that the sequence would be different from Q. So in general, what we're doing is we are adjusting the sequences on different dyadic cubes as we go so that no pair of semi-adjacent cubes will have the same digits. Or so no points inside any pair of semi-adjacent cubes in the collection CF will have the same strings of digits at the end. So another thing to observe is that for any fixed point x in our construction, the word, so alpha k at x, will only change a bounded number of times. And the reason why is because we only change the value of alpha at a point x whenever x is contained inside a cube from E1 as part of a pair from curly f, which means that the number of times that we change the value at x is going to depend on the number of cubes from E1 that contain x. But recall that because curly f are pairs of semi-adjacent cubes from E1 not contained in E2 union E1, well, by definition of E2, that implies that if we look at the point x, it will not be contained in more than n many cubes from E1. And that will imply that there is a bounded number of pairs of cubes from curly f for which one of the cubes in the pair contains x. And thus, that means that alpha k will only change at x a bounded number of times, depending on the number n. So thus, for any point x, the sequence terminates after at most n prime steps. And if it terminates before then, we just tack on a bunch of zeros to the end to complete the word to a length of zero, to a string of zeros and ones of length n prime. So that means that there are at most 2 to the n prime many such words. And then the sets ej that we just pick ej to be the set of points whose words are equal to the jth word or the jth string of zeros and ones. Our claim now is that the function f restricted to the set ej is 2 over delta bi-Lipschitz. So in order to prove this, we're going to recall the following lemma that we covered in the video on Arzela Ascoli as an example of how to use compactness arguments. So recall that it said that for any delta bigger than 0, we can find some number epsilon so that if the Hausdorff content of the image of the cube is at least delta times the Hausdorff content of the cube, and there are points x in Q and y in 10Q whose distance is at least L of Q apart, and finally that f of x minus f of y is small in the sense that it's at most delta over 2 times x minus y, then this implies that the omega number for 10Q must be at least epsilon. Okay, so let's suppose x and y are inside my set ej. I know that my function is 1 Lipschitz, so all I have to do is show the lower Lipschitz bound. Okay, so I'm going to let Q be a dyadic cube containing x, and I'm going to let it be the largest dyadic cube such that 3Q does not contain y. So let's say this is my point x, and here's the cube Q, and let's say this is my point y. So observe that if I look at the cube R of same side length as Q containing y, then Q and R are semi-adjacent to each other. Okay, but then this means that this implies that because x and y are inside the same set ej, that implies that this pair Q and R was not inside my list of pairs F, because if it were inside my list of pairs, then that would mean that I would have changed the words for x and y. So x and y would end up in 2 different sets. However, they are both in the same set ej, which means that they have the same word. So because Q and R are not inside, are not a member of our list of pairs F, recall that these pairs were lists of cubes Q and R where both Q and R were inside E1. Okay, so remember what it meant to be inside E1 was that the omega number for 10Q was at least epsilon. So because QR is not inside this list of pairs, that implies that at least one of Q or R must be so that its omega number is less than epsilon. So without loss of generality, by symmetry, we can assume that it's 10Q that has omega number less than epsilon. Okay, but then if that's the case, then by this lemma, that implies that this inequality cannot be true because because the other inequalities, that x is in q and y is in 10q and they're at least L of q apart, that's still satisfied. But because omega f of 10q is not at most epsilon, this implies by the lemma that f of x minus f of y is at least delta over 2 times x minus y, or is strictly bigger than. And that implies that f is bi-Lipschitz at all pairs of points in EJ, and that concludes the proof of the theorem.